All right, this is a video lesson for Unit 6, Lesson 3, which is two dependent means. This is a very different kind of problem than what we were doing in L2, which was independent means. You'll find that Lesson 3 is very different than the other Unit 6 lessons. It's actually a lot more similar to a Unit 5 lesson, and you'll see why pretty soon. So dependent populations. That's where this is coming from, calling it dependent means. So I'll go back to what I was using yesterday with husband and wife data. So if I have husband and wife data, let's just say how tall they are in inches. So the husband is 74 inches, the wife is 62 inches. Husband is 71 inches, wife is 65 inches, husband is 68 inches, wife is 67 inches. Okay, so there is a one-to-one link. This is the husband and this is his wife. This is the husband and this is his wife. This is the husband and this is his wife. So you'll notice with dependent that the sample sizes are going to be the same. There has to be the same number of husbands and wives or whatever the link is. And there is a one-to-one connection. So every single data value in the husband data set has to have one and only one paired up data value from the wife set. Okay? So as I said, there is going to be exactly the same size between the two populations. This guarantees that the two populations have to be the same size. And then what we're going to do is we're going to treat this as a one population problem. So we're going to create something called a difference population, where we subtract the two paired data values. We're going to subtract them and get a number, and that number is going to go into the new population. So if I were to take husband minus wife here, 74 minus 62 would give us 12. That would be the first data value in my difference population. Then I would take this 71 minus 65, and I would get 6, and 68 minus 67, and I would get 1. And we're going to use that difference population to solve this problem of, are the means the same, or are they different, or is one bigger than the other, etc. Okay, so that's a very different strategy for handling this problem, and that makes the setup harder, but then the back half of the problem is more of a Unit 5 type problem. So the method, it's actually going to be our most different hypothesis. We're going to have mu sub d, and D means difference. So we're saying the mean of the difference population, okay? And we're pretty much always going to set this equal to 0. It technically could be a number, and in a more advanced stats class, we would plug in some numbers, but that's not really important for us right now. We're really just going to say mu sub D equals 0 as the null hypothesis, which means the null is always going to be that there is no difference between the two means. The average difference is 0, meaning there is no difference between the means. That will be our null hypothesis. Our alternative hypothesis, which these are definitely the toughest alternative hypotheses to set up, our alternative hypothesis will be one of these three. Now remember, this number part is pretty much always going to be 0 for us. In other stats classes, like I said, it could be different, but for our class, it's always going to be 0. The alternative is either going to be not equal to, greater than, or less than. And you have to be really careful with these problems because it's not going to be straightforward from the wording of the problem. It's not just if you hear less than, that means this. If you hear greater than, it means this. If you hear not equal to, then it is this. But for the greater than and less than, it's actually a little bit more challenging. So after that, we can get back to what we know how to do. Test statistic, p-val, conclusion, all those rules will be the same. But the hypotheses will actually be a little bit harder to set up in these problems. Here's our test statistic. Our test statistic is going to be a t, not a z, so it'll be t-CDF when we get into the p-val. D bar is going to serve as the average difference between the two pairs of statistics. So we're not going to have like a x bar 1 or x bar 2. We're going to have what's called a D bar, which is the average difference. When you look at mu sub D, that's the average difference between the two population means This is going to come from our evidence, and we'll show you how to get that here soon. Okay, this is the standard deviation. It's going to come from our difference population, and this is the sample size of the two populations, which will also be the sample size of the difference population. What you'll notice from this formula is this is really like x bar minus mu over s divided by root n, which is the old one population t-test. So we're treating this as a one population problem using the difference population that's constructed from the two populations. So this kind of walks you through how we're going to go and get all this information, but I'm really just going to explain it to you. So if you need to look up at this and kind of see it written down as notes, go ahead, but I'm going to kind of explain it to you as we do our first example. So here's our first example, and if you notice, I've left a little bit of a space up here to go and help us with a little bit of work that we can do to help ourselves determine how the hypotheses should look. So I did that on purpose. I left a little bit of space up here on purpose for just a little bit of work. Okay, so the table below shows the weight of 7 subjects before and after following a particular diet. We want to use a 0.01 significance level to test the claim that the people have a lower weight after the diet. So this is Joe's weight before the diet. This is Joe's weight after the diet. This is Bianca's weight before. This is Bianca's weight after. That's how each of these different pairs of data values are going to work. Okay, it's a before and an after. Now, for these problems, the order of subtraction is going to make your work really matter. If you do after minus before, you can get the same answer, but all your work's going to look different until the end. So for the test, I like to tell you which order of subtraction to do. Otherwise, you have to kind of state it at the beginning of the problem because it does significantly affect the work, which order you choose to use. So what I'm going to do for our notes is I'm going to tell us, let's use before minus after. So to calculate all of these difference population values, we're going to take the before value and subtract the after value. Okay, it's not wrong to go after minus before. It's just this will allow us to be consistent with each other. So this is going to be my difference population down here. And that's what's really going to go into the calculator and all of our calculations. So 190 minus 183 equals 7. 153 minus 144 equals 9. Okay, 183 minus 181 equals 2. 161 minus 166 equals negative 5. This equals 14, this equals negative 2, and this equals 12. So those are our difference population values. These are the things that I would be putting into my calculator when we start finding our test statistics. And I will explain that when we get to that point. But that's our difference population. Now, here is the trickiest part of this entire lesson. We need to figure out what kind of value we're looking for our hypotheses. The first part is going to be easy. It's going to be mu sub d equals 0. That means that the average difference is going to be 0. That's always going to be your null hypothesis. So let's slide that over a little bit. Let's call it the null. I forgot to do that. Okay, this is our null hypothesis. Now our alternative hypothesis. Our alternative hypothesis is going to be a little bit trickier. It's going to be mu sub d, and it's going to be 0. What we need to figure out is what are we looking for? Are we looking for a negative difference or a positive difference for the claim to be true? Okay? If it's negative, we're going to say less than. If it's positive, we're going to say greater than. So let's remember, okay? This is, right over here, we're just going to say figuring out HA. Okay, when we figure out HA, what we're going to do is we're going to use the subtraction order we've chosen, which is before minus after, and we're going to pick two numbers that would fit the claim. So these don't have to be numbers from your data set. We're going to make up two numbers that would fit the claim. So the claim here, people will have a lower weight after the diet. So let's make up a number. It could be any number you want. We're making this up. This is where kids get confused. They're like, where did these numbers come from? We made them up. We're just going to make up numbers that fit the claim. So let's give this person a before weight of 100 pounds. Just a random number I chose. If the claim is true, they're supposed to have a lower weight after. So I'm going to give them any number that's lower than 100. So 90. Now, what kind of result do we get back? I get an answer of 10. So first of all, I'm just going to make a note. Two numbers we pick that fit the claim. So those were two numbers that we picked that fit the claim. Result is positive. So, because this result was positive, we want to be greater than 0. It just tells us what we're looking for. If the claim is true, you'll get a positive number. If you take any before number that's bigger than the after number and do the subtraction, you're always going to get a positive result. So we want our average difference to be greater than 0 or be positive, and that would mean the claim was true. So this is tricky for people. So one more time, walking through what I did. I took the subtraction order, before minus after. I took two made-up numbers that fit the claim. 100 as the before, and then a smaller number, 90, as the after. I did the subtraction, and I realized that I'll always be getting back positive numbers if the claim is true. That told me that my alternative hypothesis should say that I should be getting back a positive average. And that is why I decided to go with greater than for the alternative hypothesis. Now, the rest of this problem should be not easy, but easier than that. Okay, so we now can go after our significance level. Our significance level here was given to us at the beginning of the problem. It's 0.01. Our test statistic from up above, our test statistic is T equals D bar minus mu sub D over S sub D divided by root N. Now, D bar is the X bar of the difference pop. So D bar would be found by taking the difference population, these numbers, and plugging them into the calculator and finding the X bar on your calculator. So that's what I'm going to go and do. I'm going to get out my calculator. I'm going to go to Stat Edit. I'm going to clear out my L1. I'm going to start typing in these numbers. 7, 9, 2, -5, 14, -2, and 12. And then I'm going to go to Stat Calc 1var Stats. And the X bar here is my D bar. And that is 5.29. My S sub D is the S of the difference population. So same thing. I already have this value or this table filled out on my calculator. That gave me back X bar. It also gives me an S, and that is 7.16. So now I have my D bar and I have my S. So let's plug those in. D bar is 5.29. S sub D is 7.16. Now, the mu sub d came from the null hypothesis, that's 0. The n is the size of both of the populations and the difference population. At this point, we're honestly only worried about the difference population. And the difference population has 1, 2, 3, 4, 5, 6, 7 data values. So that's square root of 7. If you want to type this in easier into your calculator, you don't really need that 0. So 7.16 divided by root 7 there on the bottom. Let's type it in and see what we get. I'm going to have 5.29 divided by parentheses 7.16 divided by the square root of 7. So this problem is the hardest setup and then the easiest formula to type into the calculator. And I get 1.95. And we have our test statistic. Now we're on to our p-val. So our p-value, it's a greater than problem. So I'm going to go from 1.95 and shade to the right, which means TCDF 1.95 up to 10. And then degrees of freedom will be back to n minus 1. So that would be 7 minus 1, which would be 6. I type that into my calculator. Second vars or distribution, TCDF, 1.95, comma 10, comma 6. And I get an answer of 0.0495, which is actually a little bit too big to reject. Remember, we're going to go alpha is going to, or we're going to have p-val less than or equal to alpha. And that is 0.0495 being less than or equal to 0.01, which is false. So we will fail to reject the null hypothesis. The conclusion here is that there's not enough evidence to show that the claim is true. So now we go to the claim. Okay, so there is, let's see if I can get this to let me type. There we go. There is not enough evidence to show that the diet works. And that's truthfully what our conclusion is, because if you look at it, the average person lost 5.29 pounds using this diet. If you look up here at D bar, that was the results. The average person lost 5.29 pounds. But 7's a small sample size, and we're pretty confident that the diet works, but we're not at that 0.01 significance level. It's just a little bit too big. So honestly, I think if we had more subjects, more people, we would probably prove that the diet works. But 7 people wasn't enough to prove it. That's why we say there's not enough evidence. All right, example 2. We'll try to go a little bit faster on this one, but I really want to take my time when I do the setup with you because I know that's the hard part for a lot of you guys. Okay, so 0.05 significance level. Why waste time? Let's just throw that on down here. 0.05 significance level. Before I've even read the problem, I know my null hypothesis is mu sub d equals 0. And I know my big thing I'm going to have to figure out is whether or not this is a less than or a greater than. Unless they're nice enough to give us a not equal to problem, but I don't think that's going to happen here. Okay. Remember, if we did have a not equal to problem, it'd be the same rule. So we'd have to double our result if we got a p-value for a not equal to problem. But this isn't one of those. So at 0.05 significance level, test the claim that best actresses are younger than best actors. The age at the time of winning the award is given paired with the other winner from the same year. So what I'm going to do for this is I'm going to set my subtraction order. I'm going to use, I always like to do the first one minus the second one. So I'm going to do actor minus actress. Okay. we're going to go and find our difference population, and that's going to be negative 34. I'm just doing 28 minus 62. And that's going to be negative 9. That's going to be negative 25. That's going to be, oh, you know what? I got to flip this around. I'm going to fix it for you in your notes, but I have these in the wrong place. This is actually, let's fix this for you. This is actually actress here and actor here. Let me fix that for you. It was wrong in my notes, but it'll be right in yours, so you won't have to worry about fixing it. Okay, so let's actually change this to actress minus actor. So my mistake. Actress minus actor. All right, so actress minus actor, it's going to be the same results. Negative 34, negative 9, negative 25, negative 24, or sorry, negative 14, negative 8, negative 16, negative 31. Right, maybe I should start using a calculator. I'm trusting my brain too much. 25 minus 56. Yeah, negative 31. Negative 12. Okay, my confidence is back. Let's say negative, or oh, that's positive 2, negative 9, negative 21, negative 14. There's so many of these. Negative 9, negative 41, and 6. So that's my difference population. That's what's going to go into the calculator eventually here. Okay? Now, as far as my hypothesis goes, my alternative hypothesis, which is what I'm working for right here. As far as my alternative hypothesis goes, I'm doing actress minus actor. We are going to pick a random pair of numbers that fit the claim. The claim is that actresses are younger than the actors, the ones that win this award. So the actress, let's call her 20. If she's younger than the actor's number has to be bigger. So let's say he's 40. If I do 20 minus 40, I'm going to get back an answer of negative 20. And this tells me that I'm looking for a negative difference. I'm looking for the difference, the average difference to be negative. So that means I want a less than. If that number was positive, I would be doing a greater than. None of our claims, unless it's a not equal to, none of our claims are going to be equal to 0. You're always going to see if it's supposed to be a negative or a positive that you're looking for. So we were looking for a negative, meaning a less than. Our test statistic here is going to be d bar minus mu sub d over s sub d divided by square root of n. So let's play around with this. Let's type this into our calculator, stat edit. I'm going to put these in, negative 34, negative 9, negative 25, negative 14, negative 8, negative 16, negative 31, negative 12, 2, negative 9, negative 21, negative 14, negative 9, negative 41, and 6. Your calculator can help you count how many values that was, because I see that that's my 15th entry, so that means my n is 15. I'm going to go to stat, calc, 1var stats, type in L1. My x bar here is my d bar, so negative 15.67, minus my mu sub d is always going to be 0. And then my s sub d here, the s in my 1var stats is 12.88. And like I said, my n was 15. And however we need to, let's get that into our calculator. So not stat. Let's just go to the regular part in our calculator. We have negative 15.67 divided by 12.88 divided by the square root of 15. And that gives me an answer of negative 4.71. That's my t-value. Space myself out a little bit. My p-value, this is going to be a TCDF. It's a less than, so I'm going to go from that negative 4.71, and I'm going to shade to the left. So it's going to be negative TCDF, negative 10 up into negative 471, comma, there's 15 for n, so 14 is our degrees of freedom. That gives us a p-value of, now I'm going to second distribution on my calculator, second bars. Okay, I type in that negative 10, that negative 4.71, those 14 degrees of freedom, and I get, a small number, 0.0002. That is, I forgot to circle out my last problem. That was a fail to reject, remember? Going back to this one. This is a 0.0002 is indeed less than 0.05, the alpha. So that is a reject. And then we'll write out our conclusion here, which will be, there is enough evidence at the 0.05 significance level to show that best actresses, because that was the claim, we have to word it the way the claim did, are younger than best actors. So this is the method that you use only when there is dependent means. If they were independent means, even if they're the same sample size, if they're independent, we would use the L2 method. But for dependent problems, we can treat it as a one population problem by creating a difference population and then basically doing a unit 5 method to solve the problem. And that's it.